Picture this: an astronaut floating in the endless blackness of space, their breath steady inside the helmet, the only sound in the vacuum. Suddenly, a warning light flashes. Something's wrong. The readings are off, but there's no obvious threat, no asteroid, no malfunctioning equipment, just silence and the creeping realization that danger here doesn't always look the way you'd expect. Space, for all its breathtaking beauty, is a place where unseen hazards lurk in every shadow, where the rules of survival are written in extremes. And today, we're pulling back the curtain on 30 of the most surprising, often overlooked dangers hiding in the cosmos, threats that could turn a routine mission into a fight for life itself. We often think of space exploration as a triumph of human ingenuity, and it is. But behind every success story are countless risks, some so subtle they're easy to miss until it's too late. Imagine radiation that slips through shields like invisible knives, or temperature swings so violent they can warp metal in seconds. Think about the psychological toll of isolation, where the mind begins to play tricks in the absence of Earth's familiar rhythms. These aren't just hypotheticals, they're real challenges astronauts face, and they're just the beginning. This journey isn't just about listing hazards, it's about understanding the fragile line between exploration and survival. From micrometeoroids moving faster than bullets to the strange, untamed effects of zero gravity on the human body, each danger tells a story about the universe's indifference to our presence. But here's the thing: knowing these threats is the first step to overcoming them. So whether you're a space enthusiast, a future astronaut, or just curious about the hidden side of the final frontier, stay with us. By the end, you'll see space in a whole new light and realize just how much it takes to venture into the unknown. Cosmic radiation is one of space's most insidious threats. An invisible storm of high-energy particles that doesn't just surround astronauts but passes right through them. These aren't ordinary rays like the sunlight we're used to on Earth. They're fragments of atoms blasted across the universe by exploding stars, black holes, and other cosmic violence, traveling at nearly the speed of light. And here's the terrifying part: they slice through spacecraft walls like they're barely there, striking human cells with enough force to shatter DNA strands. We've known about this danger for decades, but its effects are only becoming clearer. Take the Apollo missions. Astronauts reported seeing flashes of light behind their eyelids, even with their eyes closed. Those weren't hallucinations, they were cosmic rays tearing through their retinas, leaving tiny trails of damage. Fast forward to today, and studies show prolonged exposure increases cancer risks, damages the central nervous system, and could even accelerate brain aging. The problem isn't just the radiation itself, it's that our best shielding often does little to stop it. Lead, which blocks radiation on Earth, can actually make things worse in space by splintering incoming particles into even more harmful secondary radiation. Current solutions are a patchwork of compromises. The International Space Station relies on its position within Earth's protective magnetic field, but venture farther, say to Mars, and that shield disappears. NASA experimenting with water-lined walls or synthetic materials that mimic Earth's atmosphere, but nothing yet matches our planet's natural defenses. The cruel irony: the very technology that lets us explore space might also be what makes it so deadly. Every minute outside Earth's embrace is a gamble with particles that have crossed billions of years just to reach us, and our bodies weren't built to pay that price. The sun isn't just the source of life, it's also one of space's most unpredictable killers. Solar flares, those sudden eruptions of radiation from the sun's surface, can unleash more energy in minutes than all of human civilization has ever produced. These aren't gentle waves of light, they're tsunamis of charged particles racing toward us at millions of kilometers per hour, capable of frying electronics, scrambling communications, and bathing unprotected astronauts in lethal radiation. History gives us chilling examples of just how close we've come to disaster. Take August 1972, when one of the most powerful solar storms ever recorded erupted right between the Apollo 16 and 17 missions. Had astronauts been in space at that moment, the radiation dose would have been deadly, enough to cause acute radiation sickness within hours. Experts later called it the bullet we dodged. Even shielded spacecraft might not have been enough. The storm was so intense it triggered geomagnetic surges strong enough to make power grids on Earth fail thousands of kilometers away. Modern technology hasn't made us invincible. A similar flare in 1989 left 6 million people in Quebec without power for 9 hours, and a 2015 near miss missed Earth by just a week. For astronauts, the danger is even more personal. Without Earth's atmosphere and magnetic field to absorb the blow, a major flare could turn a spacewalk into a death sentence, bombarding them with radiation equivalent to thousands of chest X-rays in minutes. Detection systems give some warning, usually about 24 hours, but that's not always enough to escape. NASA designed spacecraft with storm shelters, thick-walled compartments where crews can hunker down, but these are temporary fixes. On a Mars mission where help is months away, a surprise flare could strand astronauts without functional equipment or communications, the terrifying reality. The Sun operates on its own schedule, and the next big storm could already be building beneath its surface, invisible until it's too late. What makes solar flares so sinister is their duality. They're beautiful from a distance, dancing loops of plasma visible through telescopes, but up close, they're a reminder of how fragile our technology really is in the face of cosmic forces. Every satellite, every spacesuit, every life support system is just one angry sunburst away from failure. And unlike asteroids or debris, we can't dodge this threat. We can only prepare, hope, and respect the star that gives us life, but could also take it away. Floating effortlessly in zero gravity might look like fun, but what happens to the human body when it's deprived of Earth's pull for months or even years? Microgravity isn't just an absence of weight, it's a silent thief, slowly stealing the very things that keep us strong and healthy. Without the constant resistance of gravity, muscles atrophy, bones crumble, and even eyesight deteriorates in ways scientists are still struggling to understand. The International Space Station has been a living laboratory for these effects, and the findings are anything but reassuring. Take bone loss, for example. On Earth, our skeletons are constantly rebuilding themselves, a process fueled by the stress of walking, running, even just standing. But in space, that stress vanishes, and so does bone density. Studies show astronauts lose up to 1% of their bone mass every month, a rate comparable to osteoporosis patients over decades. The hips and spine, which bear our weight on Earth, are hit hardest. Even with rigorous daily exercise, some astronauts return with bones so weakened they're at risk of fractures from minor stumbles, the scariest part. Some of that loss might be permanent. Mars-bound crews could arrive with the skeletons of elderly adults, their bodies hollowed out by the journey itself. Then there's muscle wasting. Without gravity, the legs and back, the muscles that keep us upright, begin to shrink within weeks. Astronauts on the ISS spend 2 hours a day strapped into resistive machines, fighting to preserve what they can, but it's a losing battle. Imagine a marathon runner's legs withering to half their strength, not from disuse, but from an environment that renders their very purpose meaningless. By the time they return to Earth, many astronauts can't walk without assistance, their muscles so weakened they collapse under their own weight. But perhaps the most baffling effect is on vision. Nearly 2/3 of astronauts experience blurred eyesight after long missions, a condition now dubbed spaceflight-associated neuro-ocular syndrome. The leading theory: in microgravity, bodily fluids no longer pull downward, accumulate in the head, increasing pressure that flattens eyeballs and swells optic nerves. Some astronauts return with permanent changes to their prescription. Others face retinal damage that resembles glaucoma. for a Mars mission, this isn't just inconvenient, it's catastrophic. Imagine landing on another planet only to realize you can't read the controls of your own spacecraft. The deeper we venture into space, the more these effects compound. A 6-month ISS stint is one thing, a 3-year Mars mission is another. Every system in the body evolved under gravity's unrelenting tug, from how blood circulates to how the inner ear maintains balance. Strip that away and the human body becomes a stranger to itself. Countermeasures exist, but they're stopgaps at best. Artificial gravity through rotating spacecraft remains theoretical, and pharmaceuticals can't fully replicate the forces that shaped our biology over millions of years. The truth is, we're Earth creatures through and through, and space treats us like invaders, slowly, methodically dismantling us from the inside out. Space debris is an invisible minefield whirling around our planet at speeds faster than bullets, a growing cloud of destruction made up of dead satellites, spent rocket stages, and fragments from past collisions. Right now, over 128 million pieces of human-made junk orbit Earth, ranging from paint flecks to bus-sized rocket bodies, all traveling at up to 28,000 kilometers per hour. At those speeds, even a bolt the size of a marble hits with the force of a hand grenade, capable of puncturing spacecraft, disabling satellites, or shredding spacesuits. And unlike Earth's natural hazards, this one is entirely our own making. Take the infamous 2009 collision between the defunct Russian satellite Cosmos 2002-51 and the operational Iridium 33. The impact wasn't just a crash, it was an explosion, creating over 2,000 new fragments instantly. Each of those pieces became its own deadly projectile, further crowding orbits already packed with decades of discarded hardware. Scientists call this cascading effect the Kessler syndrome, a nightmare scenario where one collision triggers another, then another, until low Earth orbit becomes an impassable shooting gallery. We're already seeing the early signs. The International Space Station regularly maneuvers to avoid debris, and in 2021, a Russian anti-satellite test deliberately blew up a dead satellite, littering orbit with thousands of fresh shards that forced astronauts into emergency shelter procedures. What makes space debris uniquely terrifying is its persistence. Without atmospheric drag to slow it down, most orbital junk will stay up for decades, some for centuries. The oldest relics, like the 1958 Vanguard 1 satellite, still circle Earth today, outliving the civilization that launched them. Cleaning it up is nearly impossible. Nets, harpoons, and even lasers have been proposed, but the scale of the problem dwarfs our current technology. Meanwhile, private companies flood space with thousands of new satellites, adding to the congestion. Starlink alone plans to launch tens of thousands more, turning orbit into a high-stakes game of bumper cars where one wrong move could cripple global communications, weather forecasting, and even GPS. The ultimate irony, the very technology that connects us on Earth could eventually trap us here. If Kessler syndrome goes unchecked, we might reach a point where leaving the planet becomes too dangerous, surrounded by a shell of shrapnel that turns every launch into a gamble. Unlike radiation or solar flares, this threat isn't natural, it's a mirror reflecting our own carelessness. And unless we change course, the final frontier might become a maze of our own making, sealing us inside a cage of orbiting wreckage. One moment, a spacecraft is bathed in the unfiltered fury of the sun, its surface heating to over 150 degrees Celsius, hot enough to boil water instantly. The next, it slips into Earth's shadow, temperatures plunging to -100 degrees, colder than Antarctica's deepest winter. These aren't gradual changes, they're violent swings happening in minutes, warping metal, cracking seals, and pushing materials to their absolute limits. Unlike Earth, where oceans and air smooth out temperature extremes, space offers no mercy, just brutal, unrelenting shifts between inferno and icebox. Keeping spacecraft functional in these conditions is an engineering nightmare. Metals expand when hot and contract when cold. a simple fact of physics that becomes catastrophic in orbit. The Hubble Space Telescope, for example, was nearly crippled by thermal flexing, its solar panels warping like overcooked spaghetti as they cycled between sunlight and shadow every 90 minutes. Even the International Space Station, with its advanced thermal control system, relies on massive radiators and ammonia loops to bleed off excess heat, while electric heaters fight to keep critical systems from freezing solid. One malfunction, and the station could swing from a sauna to a meat locker in hours. The Apollo missions faced this danger head-on. The lunar module had to endure 300-degree swings between day and night on the moon, with one side baking in sunlight while the other faced the void. Engineers layered the craft in gold foil not for show, but because gold reflects heat better than almost any material. Even then, astronauts reported condensation freezing on control panels during night passes, their breathable air threatening to turn into frost on the inside of the hull. Modern spacecraft use liquid-cooled garments and phase-change materials to manage heat, but these solutions are stopgaps against a universe that doesn't care about human comfort. Perhaps the cruelest twist: shadows aren't safe havens. Without air to carry heat away, objects in shade don't just cool, they radiate stored heat into space, dropping temperatures faster than any natural process on Earth. A glove left floating too long in darkness could become brittle enough to shatter on contact. Meanwhile, indirect sunlight paints blister, adhesives fail, and electronics overheat unless constantly cooled. The James Webb Space Telescope, parked a million miles from Earth, faces this challenge daily. Its sunshield, the size of a tennis court, must block enough heat to keep instruments at -233 degrees while the sun-facing side broils at 85 degrees. One tear in that delicate shield, and $4 billion of technology becomes space junk. These extremes aren't just technical hurdles, they're reminders of how alien space truly is. Our inventions, built for Earth's gentle gradients, must survive an environment where room temperature doesn't exist. Every spacecraft is a tightrope walk between melting and freezing, where the wrong calculation can turn life support systems into useless scrap. And as we reach for Mars and beyond, the swings grow even more severe, proving that in space, even the absence of weather can be a storm in itself. Vacuum exposure isn't just a sci-fi nightmare. It's a real, gruesome threat hiding just beyond the thin metal walls of every spacecraft. Hollywood loves to dramatize it, bodies swelling, eyes bulging, explosions of frozen breath, but the reality is far more chilling and far less theatrical. In the absolute emptiness of space, where air pressure drops to zero in seconds, the human body doesn't explode, it unravels. The Soyuz 11 tragedy remains one of spaceflight's darkest warnings. In 1971, 3 Soviet cosmonauts, Dobrovolsky, Volkov, and Patsayev, were returning to Earth after a record-breaking mission aboard the world's first space station. Re-entry went smoothly, the capsule landed perfectly, but when recovery crews opened the hatch, they found all 3 men dead, strapped calmly into their seats with dark blue bruises staining their faces. A faulty valve had burst open during separation from the station, venting their cabin into space in less than a minute. The autopsies revealed the horrifying truth. Their lungs had ruptured from the sudden decompression, their blood vessels collapsed under the pressure shift, and their brains starved of oxygen within 40 seconds. They'd been conscious long enough to know what was happening, scrambling to close the valve by hand, but space offers no second chances. What makes vacuum so lethal isn't just the lack of air, it's how wrong our bodies are for it. Without pressure, the water in your saliva, tears, and even your skin begins to boil at body temperature, not from heat, but from the absence of atmospheric pressure keeping liquids stable. Your eardrums would likely burst first, a searing pain followed by deafness. Then the air in your lungs expands violently, tearing delicate tissues as it rushes out. Contrary to movies, you wouldn't freeze instantly. Space is a near-perfect insulator. so heat leaves your body slowly. Instead, you'd suffocate long before the cold became a problem, your brain shutting down from oxygen deprivation in under 15 seconds. Survival isn't completely impossible, but the window is razor thin. In 1966, a NASA test subject accidentally depressurized his suit inside a vacuum chamber. He passed out after 14 seconds but was revived with no lasting damage, proving that rapid repressurization can save a life if it happens fast enough. That's why modern spacesuits are designed with multiple redundant pressure layers, and why astronauts train relentlessly for leak scenarios. One tiny puncture, though, and those layers mean nothing. The scariest part, unlike radiation or debris, vacuum doesn't give warnings. There's no alarm for a slow leak until it's too late, no flashing light for a crack in the hull. Just silence, then agony. It's a reminder that space isn't just empty, it's hungry, waiting to erase the fragile pockets of air we carry with us. Every spacecraft is a lifeboat in an ocean with no shore, and the water outside is deadly. Imagine being trapped inside a metal box the size of a small van for 6 months, with the same handful of people, the same recycled air, the same food, and the same endless view of blackness outside your window. No wind, no rain, no new faces, just the hum of machinery and the crushing weight of knowing Earth is hundreds of kilometers below, utterly out of reach. This isn't just physical isolation. It's a psychological battleground where the human mind fights against its own hardwired need for connection, variety, and the rhythms of home. Astronauts call it the break-off phenomenon, a creeping sense of detachment, as if the thread tethering them to Earth has been severed. Some describe it as floating in a dream where time stretches and compresses unpredictably. Others report vivid hallucinations, hearing phantom voices, seeing flashes of color where none exist, or even smelling scents from childhood that couldn't possibly be there. The longer the mission, the more the mind rebels. NASA studies reveal alarming trends. Sleep disturbances, irritability, and depression spike after just weeks in space, with some crew members withdrawing into themselves or fixating on minor frustrations. Then there's the overview effect, a radical shift in perspective reported by many who see Earth from orbit. The planet transforms from a place of borders and conflicts into a fragile, glowing marble, a single, interconnected system. For some, it's euphoric, sparking lifelong environmental activism. For others, it's destabilizing, making earthly concerns feel trivial or unreal. Astronaut Rusty Schweickart described it as seeing time itself, while others return with a numbness they can't shake, struggling to reintegrate into a world that suddenly feels small and petty. The solutions being tested are as innovative as the problem is profound. Virtual reality therapy lets astronauts escape their confines, immersing in forests, beaches, or even simulated social gatherings. The International Space Station now includes private booths where crew members can retreat for video calls with therapists or family, though the 20-minute delay in deep space communication will make real-time support impossible for Mars missions. More experimental approaches include AI companions trained to detect mood shifts in speech patterns, or bioluminescent plants that change color to mimic Earth's day-night cycle. But perhaps the most critical insight comes from Antarctica's isolated research stations, where winter crews face similar mental strains. There, rituals matter, celebrating holidays, sharing meals, maintaining strict routines. The lesson: space isn't just a technical challenge, it's a social one. The right crew mix, balanced for personalities as carefully as skills, can mean the difference between cohesion and chaos. Yet no amount of preparation can fully replicate the neural cocktail of walking barefoot on grass, feeling rain, or hugging a loved one. The brain, it turns out, might be the most fragile piece of equipment we bring to space, and the hardest to repair when it breaks. This isn't just about surviving a mission, it's about returning whole. The longest spaceflight records belong to cosmonaut Valery Polyakov, who spent 437 consecutive days aboard Mir. His secret: you must love space, he insisted, but love isn't always enough. As missions grow longer, the question isn't whether we can endure the void, but what parts of ourselves we might lose in the process, and whether we'll recognize the people who come back. Moon dust isn't just dirt, it's a silent saboteur, razor-sharp and hungry to invade every crevice. During the Apollo missions, astronauts quickly discovered this wasn't ordinary soil. Tracked back into their landers on boots and gloves, the fine gray powder clung like crushed glass, scratching helmet visors, jamming zippers, and even wearing through layers of reinforced fabric. But the real shock came when they took off their helmets. Harrison Schmitt of Apollo 17 described it as lunar hay fever, a burning eyes, congested sinuses, and coughing fits that lasted days. That was just a few hours of exposure. Now imagine living in it for months. The problem starts with the dust's origin. Without wind or water to erode it over millennia, lunar particles remain jagged, their edges as sharp as freshly broken glass under a microscope. Each grain is electrostatically charged by constant solar radiation, making it cling to surfaces with unnatural tenacity. Worse, the Moon's surface is littered with nano-iron fragments from meteorite impacts, tiny, reactive shards that rust instantly when exposed to moisture. In an astronaut's lungs, that same reaction could trigger catastrophic inflammation. NASA simulations show prolonged exposure might cause conditions rivaling silicosis, the dreaded miner's lung disease that scars tissue irreversibly. Apollo samples revealed another nightmare. The dust is laced with toxic compounds like silicon dioxide and iron oxide, but in forms never seen on Earth. When tested with human cells, lunar soil simulants killed up to 90% of lung and brain cells within 24 hours. The particles are so small they bypass the body's natural defenses, embedding deep in alveoli where oxygen exchange happens. Future lunar settlers wouldn't just inhale poison, they'd carry it back indoors. The dust's static charge makes it stick to spacesuits, turning airlocks into contamination zones where every homecoming risks polluting the habitat's air supply. Solutions remain frustratingly incomplete. Current spacesuits shed dust poorly, and magnetic filtration prototypes struggle with non-metallic particles. Some propose dust rooms, airlock chambers where astronauts would be blasted with electron beams to neutralize static cling before entering. Others suggest liquid-based air showers, though water is too precious on the Moon to waste. The cruel irony: this isn't just a lunar problem. Mars dust, though slightly smoother, contains perchlorates, chemicals toxic enough to destroy thyroid function with chronic exposure. The very ground we aim to colonize might be plotting against us, one microscopic shard at a time. Perhaps the darkest twist is how little we knew until it was too late. The Apollo crews were guinea pigs in an experiment nobody planned. Their suffering alerted us to a danger that could derail permanent lunar bases before they're even built. Every footprint on the Moon kicks up a slow-moving storm, and this one won't blow over. Among the countless hazards lurking in space, one threat remains the most unpredictable because we still don't know if it exists. The possibility of alien microbes, organisms evolved under conditions utterly foreign to Earth, poses a dilemma that's equal parts scientific thriller and planetary nightmare. NASA classifies this as backward contamination, the fear that interplanetary missions might inadvertently bring home something more than rocks and data. Imagine a scenario where Martian bacteria, perfectly adapted to that planet's toxic soil, find Earth's oxygen-rich environment not just survivable but explosively fertile. The results could make every pandemic in human history look trivial by comparison. This isn't just science fiction. During the Apollo era, returning moonwalkers were quarantined for 21 days in a modified Airstream trailer, their samples handled like radioactive waste until proven safe. Today, protocols are even stricter. Mars rover drills are sterilized at 150 degrees Celsius for 36 hours before launch, and Europa Clipper's instruments will be baked to kill even the hardiest Earth microbes that might hitchhike to Jupiter's icy moon. But these measures are one-way shields. They protect other worlds from us, not the reverse. The terrifying unknown. We have no way to sterilize a returning Mars sample at the atomic level without destroying the very science we sought. The stakes crystallized in 2011 when researchers revived a 30,000-year-old virus found frozen in Siberian permafrost. The microbe, dubbed Pithevirus cybricum, was still infectious after millennia. Proof that longevity in extreme conditions isn't just possible but alarmingly common. Now consider that Mars had flowing water for over 1 billion years, far longer than it took life to emerge on Earth. If microbes persisted there, they'd likely be masters of dormancy, capable of surviving space travel inside meteorites or sample tubes. NASA Perseverance rover is currently caching Martian rocks for a future return mission, locked in titanium containers designed to withstand Earth re-entry. But no seal is perfect, and no sterilization method is foolproof against biology we've never encountered. History offers sobering parallels. When European explorers reached the Americas, they unwittingly unleashed smallpox and measles on populations with zero immunity, killing tens of millions. Now reverse that scenario. What if we're the immunologically naive ones? Alien pathogens wouldn't need to be malicious. They might simply interact with Earth life in ways no vaccine could predict. A protein folding we've never seen, a metabolic pathway that hijacks our cells. These are the invisible landmines hiding in reddish dust. Planetary Protection Officers, NASA, real-life contagion control specialists, walk a razor's edge. Too much caution could paralyze exploration. Too little might gamble with global biosafety. Their current solution: treat every extraterrestrial sample as a biosafety level 4 hazard, the same category as Ebola until proven otherwise. Future Mars astronauts may face months in isolation, their blood monitored for anomalies we can't yet define. It's a staggering thought. The greatest threat to humanity's expansion into space might not be cosmic rays or asteroid impacts, but organisms too small to see, waiting patiently in the rust-colored sands of another world. The universe's cruelest joke: we might discover we're not alone, only to realize the cosmos plays by rules we're utterly unprepared to face. Imagine shouting for help, then waiting an entire episode of your favorite show before hearing a response. That's the reality of interplanetary communication, where a simple SOS could take 20 minutes just to reach Earth and another 20 for instructions to come back. For astronauts on Mars, this isn't just inconvenient. It's a lethal game of telephone where every second of delay could mean the difference between survival and catastrophe. The math is merciless. Radio signals, the fastest thing in the universe, still crawl at the speed of light, roughly 300,000 kilometers per second. But Mars, at its closest, sits 55 million kilometers away. That's a minimum 3-minute lag one way, at its farthest over 20 minutes. Now picture a medical emergency, a burst appendix, a suit puncture, a fire in the habitat. Even if mission control responds instantly, their advice arrives too late. Apollo 13's famous crisis unfolded over days, with engineers on Earth brainstorming fixes in real time. On Mars, those same engineers would just be hearing about the explosion as the astronauts ran out of air. This delay transforms every action into a high-stakes gamble. Astronauts landing on Mars won't just be explorers. They'll be surgeons, engineers, and crisis managers rolled into one, forced to make life or death calls without Earth's guidance. Lunar missions had near-instant communication, a 2-second round trip. Mars flips that advantage into a cruel joke. Say a rover gets stuck in sand dunes. On the Moon, Houston could analyze the terrain and suggest maneuvers in seconds. On Mars, the crew would watch helplessly as hours ticked by, their million-dollar machine sinking deeper while awaiting instructions that might no longer apply. The psychological toll is just as brutal. Isolation weighs heavy enough without the added frustration of conversations that feel like speaking through molasses. Simple questions become exhausting when every exchange requires 40 minutes of dead air. Early Antarctic explorers at least had real-time radio. Mars pioneers will face a loneliness unlike anything in human history, stranded not by distance, but by physics itself, their lifeline stretched so thin it frays into echoes. Solutions exist, but they're stopgaps. AI assistants could offer instant, if imperfect, advice during emergencies, while pre-recorded training modules might cover contingencies. But no algorithm can replace human judgment when oxygen levels drop or a solar flare erupts. Some propose giving Mars crews unilateral authority over critical decisions, a staggering responsibility when every mistake echoes across millions of kilometers. The cruelest irony, this delay isn't a flaw we can fix. It's woven into the fabric of the universe, a reminder that space doesn't just challenge our technology, it mocks our very perception of time. Future Martians won't just live on another planet. They'll live in its past, their pleas for help racing across the void toward an Earth that's already moved on. A fleck of paint shouldn't be dangerous until it's moving 20 times faster than a bullet. That's the terrifying reality of meteoroids, the silent bullets of space that turn even dust-sized debris into potential killers. Unlike the dramatic asteroid collisions Hollywood loves, these micro-impacts happen without warning, striking with enough force to punch through steel like it's tissue paper. And the worst part, we often don't see them coming until it's too late. Take the International Space Station's close call in 2013. A piece of debris no larger than a pebble, likely a fragment from some long-forgotten satellite collision, slammed into one of the station's radiator panels. The hole it left was tiny, barely visible to the naked eye, but the consequences were anything but minor. The puncture caused a slow but steady leak of ammonia coolant, forcing astronauts into an emergency spacewalk to reroute the system before temperatures inside the station became unlivable. All this from an object too small to track with current technology, proving that in space, size doesn't always determine danger. Tracking these projectiles is a cosmic game of whack-a-mole. Earth's orbit is littered with an estimated 130 million fragments larger than a millimeter, yet our surveillance systems can only reliably monitor objects bigger than a softball. Even then, predictions aren't perfect. In 2021, a defunct Russian satellite shattered unexpectedly, adding over 1,500 new shards to the orbital junkyard, each one a potential hazard. The ISS now executes debris avoidance maneuvers several times a year, but these are reactions, not preventions. By the time ground radar spots a collision course, crews might have just hours to act. The physics behind these impacts is what makes them so unnerving. At orbital velocities, even a 1-centimeter object strikes with the energy of a hand grenade. Aluminum panels don't just dent, they vaporize on contact, creating a superheated plasma jet that can penetrate multiple layers. Modern spacecraft use Whipple shields, sacrificial outer walls designed to absorb and disperse these impacts, but no shield is flawless. The Curiosity rover's radiation detector was disabled by a micrometeoroid strike during its flight to Mars, a reminder that transit between planets is just as perilous as staying in orbit. Historical near-misses read like thriller plots. In 1969, Apollo 12's crew heard an ominous ding. During their return to Earth, a micrometeoroid had struck their service module, missing critical systems by centimeters. Decades later, the European Space Agency's Copernicus Sentinel-1 satellite suddenly lost power thanks to a 2-millimeter particle slamming into its solar panel. The damage, a crater the size of a dinner plate slicing through wiring like a scalpel. These aren't freak accidents, they're inevitable in an environment where everything moves at hypersonic speeds. The ultimate irony, some of the deadliest debris comes from our own exploration. Paint chips from old rocket stages, screws lost during spacewalks, even frozen droplets of astronaut urine. all become lethal when orbiting at 28,000 kilometers per hour. As private companies flood space with mega constellations like Starlink, the problem intensifies. Every new satellite is both a potential victim and a future source of shrapnel. Scientists warn we're approaching a tipping point where collisions spawn more debris, which triggers more collisions, a cascade that could render low Earth orbit unusable for generations. Protecting against this invisible hailstorm requires ingenuity worthy of sci-fi. Experimental lasers might one day zap smaller debris, nudging it into safer orbits. Nanosatellites with sticky, aerogel surfaces could act as orbital janitors, capturing specks too tiny for radar. But until then, every spacecraft and every astronaut rolls the dice with each orbit. The universe has been pelting Earth with space rocks for billions of years. Now we've added our own bullets to the storm. Fuel depletion in space isn't just about running on empty. It's a countdown to catastrophe where every drop of propellant could mean the difference between coming home and becoming a permanent fixture of the cosmos. The void offers no gas stations, no tow trucks, just the cold equations of physics deciding whether you'll ever see Earth again. And history proves even the most meticulously planned missions can flirt with disaster when fuel margins shrink too thin. Apollo 13's ordeal is etched into space lore, but the real terror wasn't just the explosion, it was the agonizing fuel calculations that followed. With their lunar module thrusters repurposed as lifeboats, astronauts had to execute a desperate mid-course correction using engines designed for gentle landings, not emergency pivots. A single misjudgment in their remaining fuel reserves would have sent them skipping off Earth's atmosphere into endless orbit. That near miss wasn't unique. During Gemini 8, Neil Armstrong and David Scott faced a harrowing spin when a stuck thruster threatened to deplete their attitude control fuel entirely. Only Armstrong's icy nerves and a reserve tank saved them from blacking out as their capsule tumbled end over end. Modern spacecraft aren't immune. In 2018, China's Chang'e 4 lunar lander entered a nerve-wracking 30-minute freefall when its descent fuel ran lower than predicted, forcing engineers to recalculate its trajectory in real time. Meanwhile, NASA Dawn probe spent its final months orbiting the dwarf planet Ceres in gradual decay, its ion thrusters sputtering on fumes until communication ceased forever. These aren't failures, they're grim reminders of how easily margins evaporate when battling gravity wells millions of miles from home. The physics behind fuel scarcity is brutally simple. Space offers no free rides. Every maneuver, from adjusting orbit to docking with a station, demands precise bursts of thrust. Miss the mark and you'll burn extra fuel, correcting errors, a death spiral of diminishing returns. Satellites like Hubble use gyroscopes to conserve propellant, but even those fail eventually. When the ISS fires its thrusters to dodge debris, it's trading precious fuel for safety, knowing each drop shortens the station's operational life. Backup systems offer scant comfort. Redundant tanks add weight, which requires more fuel to launch, a vicious cycle. Private companies like SpaceX now experiment with in-orbit refueling depots, but these remain futuristic fantasies compared to today's razor-thin margins. The cruel truth: every mission is a gamble with Newton's laws, and the house always wins. Stranded spacecraft don't get dramatic last stands. They just go silent, joining the growing cemetery of ghost ships adrift between worlds. Earth's magnetic field is like an invisible force field, shielding us from the worst of space's radiation, but step beyond its reach, and that protection vanishes instantly. For astronauts venturing to Mars, this isn't just a theoretical concern, it's a life or death calculation. The moment a spacecraft leaves Earth's magnetosphere, cosmic radiation exposure spikes to levels that could turn a 2-year mission into a cancer time bomb. Unlike the Apollo astronauts who had the Moon's short transit and Earth's magnetic tail as partial shields, Mars-bound crews face months of relentless bombardment with nowhere to hide. The numbers are staggering. On Earth's surface, we absorb about 3 millisieverts of radiation per year. A dental X-ray is roughly 0.05. On the ISS, shielded by Earth's magnetism, astronauts get around 160 millisieverts annually. But in deep space, that jumps to over 600 millisieverts, equivalent to a full-body CT scan every 5 days. Over a Mars mission's duration, that piles up to radiation doses comparable to a decade of smoking a pack a day, with DNA damage that could linger for life. The European Space Agency's ExoMars Trace gas orbiter measured these levels firsthand during its cruise phase, confirming what models had long predicted. Interplanetary space is a radiation gauntlet. What makes this especially sinister is how stealthily the damage accumulates. Unlike solar flares, which announce themselves with brilliant auroras and urgent alarms, galactic cosmic rays, the real killers arrive silently. These aren't just protons and electrons, they're atomic nuclei stripped bare, accelerated to near light speed by distant supernovas. When they smash into human tissue, they don't just ionize cells, they fragment and ricochet like microscopic shrapnel, creating cascades of secondary particles that multiply the destruction. NASA Mars Curiosity rover carried a radiation detector that revealed something chilling. Even the 6 months of transit to Mars would expose astronauts to radiation exceeding NASA career limits. The surface offers some respite. Mars' thin atmosphere blocks about half, but that's like choosing between a hailstorm and a downpour. Historical missions underscore the gamble. Apollo crews reported seeing cosmic ray flashes with their eyes closed, a phenomenon now known as light flashes in space. These weren't illusions, they were high-energy particles tearing through optic nerves, leaving microscopic scars. Later studies found Apollo astronauts died from cardiovascular disease at 4 times the rate of astronauts who never left low Earth orbit, a possible side effect of radiation damaging blood vessel linings. Meanwhile, lab mice exposed to simulated space radiation showed alarming cognitive decline, struggling with maze navigation months later. For Mars explorers, the implications are dire. Could the first footprints on the red planet come at the cost of forgotten memories? Solutions remain frustratingly patchwork. Water shielding using tanks as radiation barriers works but adds impossible weight. NASA proposed magnetic bubble technology could deflect charged particles, yet it's untested at scale. Even Mars' own weak magnetism offers no real sanctuary. Its patchy fields create radiation hotspots where protection varies wildly by location, the cruelest paradox. The very solar activity that threatens astronauts with deadly flares also helps by temporarily scattering galactic rays, meaning the safest times for solar weather are the worst for cosmic radiation. There's no winning, only calculated trade-offs. This invisible danger reshapes the entire premise of interplanetary travel. We can engineer against vacuum, temperature swings, even psychological stress, but radiation is the one foe we can't outthink with better gadgets. It's a reminder that space isn't just an environment, it's an anti-environment fine-tuned over billions of years to repel organic life. Every mission beyond Earth's magnetic embrace is a negotiation with mortality, where the price of discovery might be written in broken chromosomes and compromised health. The question isn't whether we'll go to Mars, it's what pieces of ourselves we'll leave behind in the void. Spinning a spacecraft to create artificial gravity sounds simple in theory, just like water staying in a bucket when you swing it overhead. But in practice, it's a dizzying engineering nightmare with consequences no astronaut wants to face. The concept seems flawless. Rotate a habitat fast enough, and centrifugal force pins occupants to the outer walls, mimicking gravity's pull. Yet the human body didn't evolve to live inside a centrifuge, and the side effects range from debilitating to deadly. Take motion sickness, normally a temporary nuisance on Earth, but in a spinning space habitat it becomes a constant torment. Inner ear fluid, calibrated for Earth steady 1G, gets confused when your head moves near the axis while your feet experience stronger forces. Early experiments in NASA's 20-foot rotating room proved this brutally. Test subjects vomited within minutes when the room spun faster than 10 revolutions per minute, their brains overwhelmed by conflicting signals. Even worse, some developed head movements or sickening syndrome, a chronic dizziness that persisted for days after leaving rotation. Future Mars ships might need to spin at just 2 RPM to avoid nausea, but that demands a structure over 200 meters wide to generate adequate force. Imagine building a skyscraper-sized rotating tin can just to walk without puking. Engineering failures multiply these risks exponentially. A spinning habitat is a symphony of moving parts, bearings that must last years without maintenance, seals that can't leak under relentless stress, power systems immune to rotational torque. The slightest imbalance could trigger a wobble, transforming the entire structure into a runaway top. In 2013, engineers testing a prototype rotating space station module watched in horror as vibrations caused unexpected resonance, shaking bolts loose within minutes. Had this happened in orbit, the module might have torn itself apart. Even successful designs face brutal trade-offs. Faster spin rates compact the structure but induce nausea, while slower spins require impractical sizes. There's no Goldilocks zone, just compromises that leave astronauts either sick, cramped, or both. The physics behind spinning structures hides another dirty secret: Coriolis effects. Toss a ball in a rotating habitat and it appears to curve unnaturally, a quirk that could turn simple tasks into frustrating ordeals. Pouring liquid becomes a guessing game as fluids spiral against their containers. Walking upstream against the spin direction feels like trudging through tar, while moving downstream gives an unsettling sensation of being slingshotted forward. Soviet experiments in the 1970s revealed an even stranger effect. Test animals in rotating cages developed abnormal heart rhythms, their circulatory systems stressed by inconsistent blood flow. Human trials showed similar risks: blood pools unevenly when gravity varies between head and feet, potentially causing fainting or long-term vascular damage. Current solutions are band-aids at best. The International Space Station's centrifuge experiments were scrapped due to cost and complexity, leaving astronauts to rely on tethered sleeping bags to simulate mild gravity during rest. Private ventures like Gateway Foundation propose rotating space hotels, but their designs gloss over the physiological toll. Meanwhile, NASA Mars mission plans now favor brute force, accepting zero-G's damage over spinning a fragile ship that might fail catastrophically mid-flight. The cruel irony: we've known how to generate artificial gravity since Konstantin Tsiolkovsky sketched rotating wheels in the 1920s. A century later, we still can't make it livable. Perhaps the greatest challenge isn't technical but psychological. Floating in zero-G feels alien but predictable. Spinning creates a world where the walls literally move around you. Early test subjects reported surreal disorientation watching a dropped object curve away like magic, feeling their own weight shift if they climbed up or down the habitat's curvature. Some described it as living inside a funhouse mirror where physics itself seemed broken. For Mars colonists spending months in transit, this constant sensory trickery could erode mental health as surely as microgravity decays bones. The dream of spinning habitats now hangs on a razor's edge. Slower rotations with huge diameters might work. Think spacecraft strung together by kilometer-long tethers. But deploying such fragile structures in micrometeoroid-infested space invites new disasters. Every alternative carries its own hidden tax: nausea, engineering fragility, or the sheer absurdity of building something the size of a city block just to keep breakfast down. Until we crack this puzzle, astronauts will remain trapped in a devil's choice: float toward irreversible bodily decay, or spin into a world where the walls themselves conspire against you. Fresh food in space is a luxury as rare as gravity itself. On Earth, we take for granted how easily a banana ripens or bread stays soft, but in the void, cosmic rays wage a silent war against nutrition. Those same high-energy particles that menace astronauts' cells also bombard their meals, methodically dismantling vitamins and proteins molecule by molecule. Studies show that after just 1 year in space, vitamin C in stored food degrades by up to 40%. Imagine your morning orange juice losing nearly half its potency by the time you drink it. B vitamins fare even worse, their delicate structures shattered by relentless radiation. The result, astronauts on long missions unknowingly edge toward scurvy-like deficiencies despite carefully planned diets, their bodies starved for nutrients that technically still sit on the shelf. The challenge goes beyond chemistry. Early space travelers choked down paste like meals from aluminum tubes, but modern astronauts at least enjoy thermostabilized pouches and occasional fresh deliveries. That progress hits a wall on Mars missions, where resupply rockets might arrive only every 2 years. NASA's Advanced Food Technology Lab now experiments with vacuum-sealed meals that last 5 years, but taste tests reveal another crisis: psychological fatigue sets in long before expiration dates. Apollo astronauts revolted against repetitive menus, hiding disliked items in storage compartments. On Mir, cosmonauts traded entire meals for single precious onions or garlic cloves, their cravings for sharp flavors overwhelming ration discipline. When Skylab's freezer failed in the 1970s, crews faced weeks of lukewarm, textureless purees, an ordeal one astronaut compared to eating baby food through a straw forever. Solutions walk a razor's edge between science and psychology. The ISS now cultivates small batches of leafy greens, more for morale than sustenance. A single bite of fresh lettuce becomes a sacred ritual after months of reconstituted meals. Future Mars ships might grow nutrient-dense microgreens under LED lights, but the energy trade-offs are staggering. Meanwhile, 3D-printed space pizza prototypes hint at customized nutrition, yet can't replicate the visceral comfort of recognizable food. The cruel paradox: the very technologies preserving food safety, irradiation, vacuum sealing, extreme dehydration, also strip away the aromas and textures that make eating joyful. Perhaps the most underrated danger is how food monotony erodes mental resilience. Naval submarines and Antarctic stations prove even well-fed humans spiral into depression when denied culinary variety. Space amplifies this. Without gravity, smells diffuse poorly, taste buds dull, and sinuses swell, leaving every meal tasting like cardboard. NASA food scientists now engineer flavor-burst gels to combat sensory deprivation, but no gel can replace the cultural weight of breaking bread together. For Martian colonists, years of eating the same 20 rehydrated meals might become the ultimate test of endurance, not just surviving on calories, but fighting to remember why eating ever mattered at all. The universe, it seems, won't just starve us in space, it'll make sure we stop caring. Fire in space doesn't burn, it creeps. That terrifying lesson seared itself into astronaut Jerry Leininger's memory during the 1997 Mir space station disaster, when a malfunctioning oxygen generator ignited into a writhing sphere of flame. Trapped in the confined module with 2 Russian crewmates, Leininger watched in horror as the fire defied every Earth-based instinct. Instead of rising upward, the blaze formed a glowing demonic halo around the ceiling, fed by superheated gases that refused to dissipate. The crew fought back with foam extinguishers, but microgravity transformed their counterattack into a slow-motion nightmare. Every burst of suppressant simply floated away in useless globules while the inferno burned for 14 excruciating minutes. This wasn't just an accident, it was a preview of how catastrophically wrong fire behaves when freed from gravity's rules. The physics behind space fires would baffle any earthly firefighter. On Earth, heat rises because hot air expands and becomes buoyant, a principle that guides everything from campfires to skyscraper evacuation plans. But remove gravity and that fundamental law dissolves. Flames don't climb, they form eerie, slow-burning spheres around their fuel source, feeding on oxygen without the natural convection that normally fans terrestrial fires. NASA experiments aboard the International Space Station reveal even more unsettling behaviors. Some microgravity fires burn at lower temperatures but refuse to extinguish, smoldering stubbornly in conditions that would snuff them out instantly on Earth. A dropped match in a space station doesn't just risk igniting materials, it risks creating a self-sustaining fireball that lingers like a malignant tumor in the confined air. Historical precedents paint an even grimmer picture. Before Mir, the Apollo 1 crew never made it to space, perishing in a horrific ground test fire that demonstrated how pure oxygen environments turn small sparks into instant conflagrations. After Mir, the ISS faced its own close call in 2013, when an ammonia coolant leak nearly mixed with electrical sparks that could have ignited a toxic inferno. These incidents share a common thread: spacecraft designs that underestimated fire's adaptability. Materials rated flame-resistant on Earth, like the aluminum and fiberglass composites used in early modules, become unpredictable kindling when exposed to long-duration microgravity flames. Modern solutions walk a tightrope between safety and practicality. The ISS now employs multiple fire zones with quick sealing hatches, but these are useless if the fire starts during a crucial experiment requiring open passage between modules. Extinguishers use watery gel instead of powder to avoid clogging air filters with particulate, yet effectiveness remains spotty against three-dimensional fires that wrap around equipment. The cruelest irony: some of the best fire suppression tools are also deadly to humans, like nitrogen flooding systems that would suffocate astronauts while smothering flames. Future missions compound these risks exponentially. A Mars-bound vessel can't vent burning modules into space like the ISS might. Every cubic centimeter of air is precious. Colonies using high-oxygen terraforming tech could turn entire habitats into tinderboxes where a single spark triggers cascading explosions. Even the Moon's 1/6 gravity creates bizarre hybrid flames that partially rise but also spread laterally with terrifying speed, as demonstrated by NASA's recent lunar habitat fire tests. The Mir crew survived by sheer luck. Their fire burned out before breaching the hull, but not before searing the station's interior with toxic fumes. That near disaster revealed space's cruelest truth about fire. We've built entire spacecraft around physics that simply doesn't apply once the engines cut off. Every wire, every oxygen tank, every piece of clothing becomes a potential fuel source in an environment where flames rewrite their own rules. Until we crack how to starve fires without starving crews of breathable air, every space mission will carry an invisible passenger. The knowledge that one spark could rewrite history in ways no emergency protocol can fully anticipate. A spacecraft's electronics might seem secure behind layers of reinforced shielding, but there's an invisible threat that slips through like a ghost: electromagnetic interference. Whether from a solar storm's fury or a single sparking wire, these chaotic energy surges can turn mission-critical systems into useless junk with no warning. Imagine your car's GPS, radio, and engine computer all failing at once during a highway merge. Now picture that panic multiplied by the vacuum of space, where backup options vanish faster than oxygen in a hull breach. The most dramatic culprit: solar flares. When the sun spews a coronal mass ejection, it doesn't just bring radiation, it floods space with electromagnetic noise strong enough to overpower even hardened circuits. In 1989, a flare-induced power surge blacked out Quebec within 90 seconds. Satellites fared worse. NASA TDRS-1 communication satellite lost half its attitude controls to an electromagnetic pulse, while others recorded memory bits flipping autonomously as if haunted. Modern spacecraft use Faraday cages and error-correcting chips, but Mars-bound crews won't have Earth's magnetic field to blunt these attacks. The result could be navigation systems glitching mid-course correction or life support computers resetting unpredictably, all while millions of miles from help. Equipment failures pose just as much danger without the drama of solar storms. The International Space Station has suffered multiple close calls from electromagnetic noise bleeding between modules. In 2001, a Russian computer crashed repeatedly due to interference from newly installed American hardware, forcing temporary manual control of the station's orientation. More chilling was the 2016 incident where a static discharge near the oxygen generators mimicked sensor failures, nearly triggering an emergency shutdown of the primary life support system. These aren't isolated bugs, they're symptoms of an environment where every wire and device broadcasts invisible interference in confined metal halls. What makes electromagnetic interference uniquely terrifying is its invisibility. Unlike a fire or decompression, there's no smoke, no alarm, just displays freezing or thrusters firing randomly. The Apollo 12 launch demonstrated this horrifyingly when lightning struck the rocket twice during ascent, scrambling the command module's computers. Only pilot Alan Bean's memorized reset procedures saved the mission. Today's vehicles face a subtler version of this threat. Wireless signals from astronauts' own tablets have disrupted experiments, while stray Wi-Fi emissions could theoretically hijack unshielded medical devices. Countermeasures walk a tightrope between protection and practicality. The ISS now employs strict electromagnetic hygiene protocols separating high-power cables from sensitive lines, using fiber optics instead of copper where possible, and enforcing radio silence during critical operations. But the ultimate nightmare remains a blackout event where interference cascades through multiple systems simultaneously. During a 2018 test, engineers simulated a solar flare hitting a Mars habitat's power grid. The resulting feedback loops crashed everything from water recyclers to door motors in under 3 minutes. No current shielding fully blocks such wide-spectrum assaults, leaving future colonists one bad solar day away from reverting to pen and paper while their machines scream gibberish. This danger doesn't just threaten machines, it rewires human instincts. Pilots train to trust their instruments, but what happens when those instruments lie? Air France Flight 447's crash proved how quickly crews unravel when conflicting sensor readings create impossible dilemmas. In space, where every decision relies on electronics, electromagnetic interference could manufacture crises from nothing: fake pressure leaks, phantom engine failures, or navigation showing Earth as suddenly 500 kilometers off course. The mind rebels against such paradoxes, and in the void, that split-second hesitation could be fatal. The universe doesn't just attack astronauts with radiation and debris, it hacks their very perception of reality. Time dilation sounds like pure science fiction, a quirk of physics reserved for wormholes and warp drives. But this mind-bending effect is very real, and for future astronauts pushing the boundaries of speed, it could mean returning to an Earth that's aged decades without them. Einstein's theory of relativity isn't just abstract math. It dictates that time slows down for objects moving at extreme velocities or enduring intense gravity. The difference might be negligible for today's spaceflights, but as we inch toward interstellar travel, this hidden danger could fracture human connections in ways no training can prepare for. Consider the iconic twin paradox. An astronaut traveling near light speed to a nearby star might experience just a few years passing, while their Earth-bound twin grows old and gray. This isn't hypothetical. GPS satellites already compensate for time dilation, their clocks ticking microseconds faster than Earth's due to orbital speeds. The effects are tiny now, but scale them up to a hypothetical 95% light speed Mars mission, and the numbers get eerie. A 2-year voyage for the crew might mean 2.5 years passing on Earth. Stretch that to a Proxima Centauri trip, and decades of separation stack up. The first interstellar explorers could return to find their grandchildren older than they are, their world reshaped by technologies and politics they never witnessed. Gravity's role is even stranger. Near a black hole's event horizon, time crawls so slowly that an outside observer would see astronauts moving in slow motion before freezing entirely. While we're not sending crews into black holes, this principle still haunts long-term planetary missions. Mars' weaker gravity means time there flows slightly faster than on Earth, about 36 microseconds per day. That's trivial now, but for permanent colonists, those microseconds compound into seconds, then minutes over generations. Future Martian metropolises might need their own time zones just to stay synchronized with Earth's financial markets or diplomatic communications. The psychological toll could dwarf the technical challenges. Imagine watching video messages from home where loved ones visibly age between transmissions, or realizing your childhood home was demolished years ago in Earth time while you were en route. Early Antarctic explorers suffered depression from isolation, but at least their world stood still. For relativistic travelers, time itself becomes the enemy, stretching social bonds beyond recognition. Cryogenic sleep, a sci-fi staple, wouldn't solve this. It would just outsource the loneliness to AI pilots keeping the ship on course. Current tech keeps this danger in the realm of theory. Even NASA Parker Solar Probe, the fastest human-made object at nearly 700,000 kilometers per hour, experiences just milliseconds of dilation over years. But private ventures like Breakthrough Starshot aim to propel nanocraft to 20% light speed within decades. If scaled for crewed ships, such speeds would make time dilation unavoidable. The cruelest twist: there's no workaround. Physics offers no loophole for nostalgia. Every tick of the ship's clock is a step further from the world you left behind, a one-way trip into humanity's future, whether you're ready or not. Astronauts may look like they're getting a workout strapped to space treadmills, but those bungee cords and resistance machines are barely holding back an inevitable decline. In microgravity, muscles wither at an alarming rate, up to 20% loss in just 11 days, despite crews spending 2 grueling hours a day fighting against harnesses and elastic bands. The problem isn't effort, it's physics. Earth's gravity provides constant resistance, from walking upstairs to lifting a coffee cup. In space, even the most advanced exercise equipment can't replicate that relentless force, leaving astronauts to pedal and squat in a losing battle against their own biology. Take the celebrated Advanced Resistive Exercise Device, or ARD, aboard the International Space Station. This high-tech weightlifting substitute uses vacuum cylinders to simulate loads up to 600 pounds, but there's a catch. Without gravity's directional pull, muscles work in unnatural patterns. On Earth, standing engages calves, thighs, and core simultaneously. In space, strapped into ARD, astronauts isolate muscle groups mechanically, missing the integrated coordination that keeps terrestrial bodies functional. The result: returning astronauts often struggle with basic tasks like climbing stairs, their muscles rebuilt in disjointed fragments rather than as cohesive systems. Bungee treadmill running reveals another cruel joke. Videos show astronauts jogging in place, tethered by elastic cords to mimic body weight. But these setups can't reproduce the ground reaction forces that strengthen bones and connective tissues during real running. Studies of cosmonauts on year-long missions revealed persistent muscle deterioration even with daily treadmill use, their calf muscles shrinking to nearly half their pre-flight size. The deceptive danger: these workouts create an illusion of normalcy while masking deeper atrophy. Like a fish trying to bench press in air, the body knows something's off, no matter how hard it strains against the straps. The limits of current countermeasures became starkly clear during NASA, a twin study. Astronaut Scott Kelly returned from a year in space with post-flight MRI scans showing significant spinal muscle shrinkage despite rigorous exercise. His ground-bound twin Mark, meanwhile, maintained normal muscle composition. The difference, Earth's constant 1G load, a subtle background radiation of resistance that no machine fully duplicates. Even vibration plates and flywheel devices designed to stimulate fast-twitch fibers can't compensate for the absence of gravity's 24/7 challenge. Future Mars missions amplify these risks exponentially. 6 months to Mars means 6 months of muscle fibers unlearning their earthly purpose, even as astronauts perform daily workouts in a ship that may lack the ISS's spacious gym. Proposals like centrifuges or rotating habitats remain theoretical, leaving crews to rely on evolved versions of the same flawed equipment. The bitter irony. We've conquered rocket science only to be thwarted by the most mundane human activity standing up. Until we crack true artificial gravity, spacefarers will keep strapping in, sweating through routines that delay but can't defeat the slow unraveling of their strength. The treadmill keeps turning, but the body remembers what it's lost. Every astronaut knows the golden rule of spaceflight. In orbit, yesterday's coffee becomes tomorrow's drinking water. The International Space Station's urine recycling system is a masterpiece of survival engineering, distilling sweat, breath moisture, and yes, even pee into crystal-clear hydration. But when this closed-loop life support stutters, the line between sustainability and crisis shrinks to the width of a failed O-ring. The process sounds simple enough. Urine gets vacuum distilled, filtered through ion exchange resins, then blasted with ultraviolet light to kill bacteria. What comes out meets purity standards stricter than most earthbound bottled water. But the reality is far messier. In 2009, astronauts tasted the consequences firsthand when a recycling unit's sensor failed, flooding the system with concentrated brine instead of fresh water. The crew suddenly found themselves guzzling emergency reserves while engineers scrambled to diagnose why their $250 million coffee maker smelled like a chemical spill. Mechanical failures aren't the only threat. Psychological barriers prove just as stubborn. NASA early studies revealed even seasoned astronauts struggle to drink water they know came from a crewmate's bladder, despite lab tests showing it's cleaner than mountain springs. This yuck factor becomes dangerous during recycling malfunctions, when crews might unconsciously ration their intake rather than tap into limited emergency supplies. The Skylab 4 mission nearly ended in dehydration when astronauts, repulsed by their malfunctioning toilets' output, drank less than half their daily requirements until ground controllers intervened. The stakes skyrocket for Mars missions where resupply is impossible. A single faulty pump in transit could leave astronauts choosing between drinking reclaimed urine with floating particles or risking kidney stones from dehydration. Engineers now test systems by introducing worst-case contaminants from toothpaste foam to simulated vomit, but space adds variables no lab can replicate. In 2022, ISS filters clogged unexpectedly with calcium deposits from astronaut urine, a side effect of bone loss in microgravity that Earth tests hadn't predicted. Perhaps the cruelest twist is how failure cascades. A urine processor breakdown doesn't just threaten hydration, it overloads waste storage, stresses backup systems, and if leaks occur creates floating biohazards in microgravity. Mere cosmonauts once battled a rogue yellowish blob drifting between modules, later identified as crystallized urea from a faulty recycler. Future lunar bases might face even uglier scenarios when trying to recycle water in 1/6 gravity, where liquids behave unpredictably. Salvation could come from unexpected places. Researchers now experiment with bioelectrochemical systems where bacteria break down waste while generating electricity, and nanomaterials that filter at the atomic level. But until these mature, astronauts remain one clogged filter away from an impossible choice: drink the rainbow or die of thirst. The universe mocks our delicacy up here. Survival has always been a dirty business. While Mars dust storms rage across the entire planet like a slow-motion hurricane, the Moon's dust behaves more like a silent, ghostly mist, both equally deadly in their own ways. Remember the harrowing sandstorm from The Martian that stranded Mark Watney? Those Hollywood visuals weren't far off. Martian storms can indeed engulf the entire planet for months, with winds reaching 100 kilometers per hour. But here's the twist. Mars' atmosphere is so thin those hurricane-force gusts feel like a gentle breeze, barely able to knock over a feather. The real danger isn't the wind, it's what it carries. Billions of razor-sharp dust particles, finer than flour, infiltrate every crevice, sandblasting solar panels into opacity and grinding mechanical joints into useless scrap. NASA learned this the hard way when the Opportunity rover met its end in 2018. A global dust storm blocked sunlight for months, starving the rover's solar panels until its batteries drained into eternal silence. Engineers designed Opportunity to survive 90 days. It lasted 15 years, but not even its ruggedness could overcome a sky turned solid orange by floating particulates. Future human habitats face an even grimmer scenario: storms that blot out the sun for weeks, forcing reliance on nuclear power while dust cakes every external sensor and window. The dust itself is laced with toxic perchlorates, chemicals that attack thyroid function if inhaled. A single breached airlock during a storm could turn a habitat into a death trap, its filters overwhelmed by an endless tide of poison powder. Now shift to the Moon, where storms don't exist, yet the dust is somehow more sinister. Without wind or weather, you'd expect lunar regolith to sit undisturbed. Instead, it levitates. Solar radiation charges dust particles with static electricity, making them cling to surfaces with unnatural tenacity. Apollo astronauts found their suits caked in gray powder after short moonwalks, the grit jamming zippers and scratching visors despite vacuum-sealed closures. This isn't ordinary dirt, it's fractal-edged shards created by eons of meteorite impacts, each grain sharper under a microscope than volcanic glass. The real nightmare begins at sunrise on the Moon. As sunlight hits the surface, electrostatic forces send dust flying kilometers high in eerie, horizon-hugging clouds. Lunar probes have photographed this phenomenon for decades, a slow-motion blizzard with no snow. For astronauts, this means every dawn brings a wave of charged particles seeking out equipment, lens surfaces, and even lung tissue if trapped inside. Unlike Mars' dramatic storms, the Moon's dust assault is silent, invisible, and relentless. A single grain could short-circuit a rover's electronics or abrade a spacesuit's knee joint until it fails mid-mission. Solutions remain maddeningly elusive. Mars explorers might deploy ultrasonic dust cleaners, vibrating panels at frequencies that repel particulates, while lunar bases could use electron beams to discharge static cling before dust infiltrates airlocks. But these are stopgaps against environments that have spent billions of years perfecting their abrasiveness. The cruel paradox: these dusts are geological archives, priceless records of solar system history, yet they wage war against the very machines sent to study them. Whether it's Mars' drowning storms or the Moon's phantom clouds, one truth emerges: the dust isn't just on these worlds, it is these worlds shaping every moment of exploration with patient, grinding persistence. Luca Pomitano should have been focused on routine maintenance outside the International Space Station, not fighting for his life. 16 minutes into his spacewalk in July 2013, the Italian astronaut felt cold water pooling at the back of his helmet. At first, he assumed it was just condensation, annoying but harmless. Then the liquid crept forward, covering his ears. Within minutes, it blinded his eyes, filled his nose, and began drowning him in the vacuum of space. This wasn't just a malfunction, it was every astronaut's nightmare playing out in real time, proving that even the most rigorously tested equipment can betray you when failure isn't an option. The cause was as mundane as it was terrifying. A clogged filter in the suit's cooling system had backed up drinking water into Parmitano's helmet. Engineers later recreated the failure on Earth, watching in horror as 2 liters of water gushed into a test helmet in under 30 minutes. In space, that same water formed a suffocating bubble around Parmitano's head, its surface tension holding it in place like a liquid jellyfish. Microgravity turned a simple leak into an existential threat. On Earth, water would drain downward. In orbit, it envelops. Parmitano's calm under pressure became legendary. Unable to see or hear, he relied on muscle memory to follow his safety tether back to the airlock, mentally counting handholds as the water sloshed against his face. His commander, Chris Cassidy, later described the horrifying sight of water completely covering his eyes, his nose, his mouth through the helmet visor. Only sheer luck prevented total catastrophe. Had the water reached the suit's electrical systems, it could have short-circuited critical life support mid-spacewalk. This near disaster exposed a chilling truth. Spacewalks are always one tiny component failure away from tragedy. Parmitano's suit had passed every pre-flight check. The flaw emerged only under the stresses of actual use, a reminder that no simulation fully replicates the chaos of real space conditions. Other close calls read like a catalogue of horrors. In 1965, cosmonaut Alexei Leonov's suit ballooned so severely during history's first spacewalk that he couldn't re-enter his capsule, forcing him to dangerously vent oxygen to squeeze back in. Decades later, in 2001, NASA Robert Curbeam discovered his gloves were losing pressure mid-EVA, a slow leak that could have led to explosive decompression if unchecked. Then there's the silent menace of suit creep, micro tears in fabric joints that develop over multiple uses, invisible until a critical failure occurs. Modern suits incorporate hard-won lessons from these disasters. Parmitano's near drowning led to redesigned helmet absorbent pads and redundant water sensors. But the fundamental vulnerability remains. A spacesuit is a miniature spacecraft with zero redundancy for its wearer. Each joint, seal, and valve must function perfectly every time because in the void, there's no removing the helmet to wipe your eyes, no pressing pause to fix a faulty hose. Future lunar and Mars missions amplify these risks exponentially. Moon dust's abrasiveness could degrade suit materials faster than Earth orbit testing predicts, while Mars cold translates to stiff, brittle joints at -60 degrees. NASA Next-Gen XEMU suits aim to address these threats with self-sealing materials and improved mobility, but no design can eliminate the human factor. A single distracted moment, a snagged glove on a sharp edge, an improperly secured visor, could unravel years of preparation in seconds. The cruel paradox of spacesuits is that they must be both robust and flexible, protective yet mobile enough for precise work. Every improvement in one area often creates vulnerabilities elsewhere. Lighter materials might resist punctures but conduct temperature poorly. Enhanced mobility joints could trap abrasive dust. Even the act of bending a knee repeatedly in microgravity wears out bearings in ways ground tests fail to predict. Parmitano survived by keeping his cool in a scenario no training could fully prepare him for. His ordeal forced a radical rethink of spacewalk protocols now. The slightest hint of moisture triggers immediate abort procedures. But the deeper lesson lingers. In space, danger doesn't always come from the void outside the suit. Sometimes it's the life-saving system inches from your face that turns against you, proving that survival hangs not just on technology, but on the fragile human ability to adapt when that technology fails. Imagine returning from space only to discover your skeleton has aged decades in just months. That's the brutal reality of bone density loss in microgravity, a silent thief that steals calcium from astronauts' bones at rates that would take elderly patients 20 years to match. On Earth, our bones constantly rebuild themselves in response to gravity's unrelenting tug. but remove that force and the demolition crew takes over without the builders ever showing up. Studies show astronauts lose 1 to 2% of bone mass every month, a staggering figure when you consider osteoporosis patients on Earth lose half that amount annually. The hips and spine, which bear our weight daily, deteriorate fastest, leaving some crew members with the brittle bones of 70-year-olds by mission's end. What makes this degeneration so sinister is how it hides in plain sight. Unlike muscle atrophy, which astronauts combat with daily resistance workouts, bone loss occurs at the cellular level with no outward symptoms. The culprit, osteoclast cells that break down bone tissue, go into overdrive while their bone-building counterparts, osteoblasts, slack off. A twin study revealed astronaut Scott Kelly's bone turnover markers spiked alarmingly during his year in space, his body essentially digesting its own skeleton. Even more disturbing, some of that damage might be permanent. Follow-up scans showed portions of Kelly's bones never fully recovered, leaving behind what radiologists call microscars, weak points where fractures could initiate under stress. The consequences crystallized painfully for astronaut Heidemarie Stefanishin Piper. During her 2006 post-flight medical exam, doctors recorded something terrifying. A routine jump test left her with multiple spinal compression fractures. She hadn't fallen or tripped, just the impact of landing under Earth's gravity was enough to crack vertebrae that had turned porous like Swiss cheese. Similar cases plague returning cosmonauts, with some unable to walk unassisted for weeks as their skeletons relearn how to handle weight. Countermeasures walk a razor's edge between effectiveness and practicality. The International Space Station's odd advanced resistive exercise device mimics weightlifting by using vacuum cylinders, but it's an imperfect fix. Earth-bound weightlifters benefit from gravity's omnidirectional pull. Odd users only stress bones along specific vectors. Nutritional supplements help astronauts now take vitamin D cocktails and bisphosphonates osteoporosis drugs, but these merely slow the decline. The cruel paradox. The very supplements preserving bone density risk causing kidney stones due to increased calcium excretion in urine. Mars missions could turn this slow burn into a full-blown crisis. 6 months to Mars means astronauts arriving with potentially 36% less bone mass in critical areas. Planetary surfaces offer partial relief. Mars' 1/3 gravity might allow some recovery, but landing after months in 0 G could be catastrophic. Picture explorers stepping onto Martian soil only to collapse with stress fractures in their hips or shatter a heel bone during their first jump. Even if they avoid acute injury, chronic pain from vertebral collapse could render them ineffective for surface operations. The medical mysteries deepen when examining where bone vanishes. High-resolution scans reveal microgravity doesn't erode bones uniformly, it hollows them from the inside like termites devouring wood. Trabecular bone, the spongy interior crucial for shock absorption, disappears fastest. This explains why astronauts pass strength tests. Compact outer bone remains somewhat intact yet crumble under impact loading. Soviet experiments in the 1970s showed cosmonauts' bones became so brittle they could snap from sudden twists, a terrifying prospect for Mars colonists handling heavy equipment. Emerging technologies offer glimmers of hope. Vibration plates that stimulate bone growth through high-frequency oscillations show promise in bed rest studies mimicking microgravity. Pharmaceutical breakthroughs like sclerostin inhibitors may one day trick bones into rebuilding despite the absence of mechanical stress. But the ultimate solution, artificial gravity through rotating habitats, remains decades away from practical implementation. Until then, spacefarers pay a skeletal tax with every mission, their bodies mortgaging future health for present exploration. The tragedy, we evolved as creatures of gravity, our very DNA wired to expect its constant presence. Strip that away and the scaffold of our being quietly dissolves, leaving astronauts to carry the cost long after their boots touch solid ground again. Floating in space might look peaceful, but the reality is closer to trying to sleep inside a creaky submarine while someone flashes strobe lights through the window every 45 minutes. Astronauts aboard the International Space Station average just 6 hours of shut-eye per night, a chronic sleep deprivation that would ground most airline pilots. The reasons read like a torture manual: incessant machinery noise, the psychological weight of living in a lethal environment, and a sunrise every 90 minutes that scrambles circadian rhythms beyond recognition. Start with the noise, an unrelenting soundtrack of whirring fans, humming computers, and clanging metal that never stops. The ISS isn't just a spacecraft, it's a life support factory where air circulators, coolant pumps, and gyroscopes operate around the clock. Sound levels hover around 65 decibels, equivalent to a running vacuum cleaner. Earplugs help, but they can't block the vibrations transmitted through the station's structure, rattling skulls like a subtle, never-ending earthquake. Former astronaut Scott Kelly described nights where he'd finally doze off, only to be jolted awake by the sudden roar of docking thrusters or the metallic groan of solar panels adjusting to temperature swings. Then there's the light. On Earth, our brains rely on consistent day-night cycles to regulate melatonin production. The ISS, zipping around Earth 16 times a day, treats crews to a sunrise every 45 minutes. Window shades block some light pollution, but subtle blue glow from control panels and experiment racks seeps into sleeping pods, tricking the brain into thinking it's perpetual dawn. NASA engineers have tweaked light spectrums to mimic terrestrial cycles, but no LED can replicate the total darkness of a rural night. The result: astronauts' melatonin levels drop by up to 40%, leaving them trapped in a twilight zone between alertness and exhaustion. Stress acts as the silent third thief of sleep. Imagine trying to relax while knowing a single hull puncture or ammonia leak could turn your bedroom into a death trap. Brain scans of astronauts show hyperactive amygdalae, the fear centers, even during rest periods. Dr. Laura Barger, who studied sleep patterns in space, found crews average 30 minutes less sleep pre-spacewalk due to anxiety, their brains too busy rehearsing emergency procedures to power down. The physiological toll compounds over time. Sleep-deprived astronauts make 50% more mistakes during simulations, a terrifying statistic when errors can mean explosive decompression. Historical near misses prove this isn't hypothetical. During the 1996 shuttle mission STS-78, fatigued astronauts botched a critical radar alignment, nearly causing a collision with a satellite. More recently, ISS crews mislabeled urine samples for a bone loss study after chronic sleep disruption impaired their attention, wasting months of research. The irony is brutal. Scientists need pristine data on space's effects on the human body, but the very act of collecting that data becomes corrupted by the conditions they're studying. Countermeasures walk a tightrope between practicality and desperation. Some astronauts resort to prescription sleep aids, risking dependency in an environment where midnight emergencies demand sharp reflexes. Others cling to rituals, watching Earth through windows or listening to pre-recorded nature sounds, but these are band-aids on a hemorrhage. The newest hope comes from flexible sleep pods that cocoon crew members in noise-dampening materials, though early tests show limited success against the station's structural vibrations. The deeper tragedy: this insomnia follows astronauts home. Post-mission studies reveal many develop chronic sleep disorders, their circadian rhythms permanently altered by months of artificial cycles. Like shift workers cranked to cosmic extremes, they pay the price long after landing. Future Mars missions amplify these risks. Imagine 6 months of disrupted sleep before arriving at a planet where days are 39 minutes longer than Earth's, forcing yet another brutal adjustment. Space agencies now treat sleep as mission-critical as oxygen levels or radiation shielding. But the universe seems indifferent to human needs, offering no natural rhythm except the cold mathematics of orbits. Until we crack artificial gravity or build rotating habitats with proper night cycles, astronauts will remain prisoners of a schedule written by physics, not biology, drifting through endless false dawns, chasing rest just beyond their grasp. Cosmic rays don't just bombard astronauts' bodies, they target the mind itself. Groundbreaking research reveals these high-energy particles may carve microscopic scars through brain tissue, triggering cognitive declines that resemble early-stage dementia. Imagine embarking on a 3-year Mars mission only to arrive with your memory fraying, your focus dissolving like sand through fingers. This isn't speculative fiction. It's the horrifying data emerging from labs where scientists simulate space radiation's toll on neural networks. The evidence first crystallized in NASA-funded studies at UC Irvine. Researchers exposed mice to ionized oxygen and titanium particles, stand-ins for galactic cosmic rays, at Brookhaven National Laboratory's Particle Accelerator. Within months, the animals showed startling deficits. They struggled to recognize objects they'd encountered before, froze in maze sections they'd previously mastered, and displayed hyperactive anxiety in open spaces. Autopsies revealed the cause. Radiation had pruned dendritic branches, the delicate neural filaments that brain cells used to communicate. Worse, it activated microglia, the brain's cleanup crew, into a destructive frenzy, literally inflaming neural tissue in a process eerily similar to Alzheimer's. Translated to humans, these symptoms could mean astronauts forgetting emergency protocols or misjudging landing calculations mid-mission. Human data, though scarcer, paints a parallel picture. Apollo astronauts, the only humans to spend days beyond Earth's magnetic shield, developed cardiovascular diseases at 4 times the rate of low Earth orbit crews. While this was initially blamed on radiation damage to blood vessels, subsequent brain scans hinted at deeper neurological tolls. MRIs showed white matter abnormalities resembling those seen in patients with mild cognitive impairment, alongside slowed processing speeds on cognitive tests. One chilling theory suggests cosmic rays preferentially damage the hippocampus, the brain's memory center, where new neurons are born. Lose that regenerative capacity in deep space, and you don't just risk forgetfulness, you risk an eroded sense of self. The mechanics of this damage are what make it so insidious. Galactic cosmic rays aren't mere protons. They're iron and silicon nuclei stripped of electrons, hurtling at near light speed. When these He particles tear through brain tissue, they don't just ionize molecules. They leave nanoscale shrapnel trails, fracturing nearby cells with secondary radiation bursts. Computer models show a single He particle can trigger oxidative stress in thousands of neurons along its path, a cascade that continues months after exposure. It's like tossing a grenade into a forest. The initial blast is destructive, but the lingering fires reshape the landscape. Solutions lag far behind the threat. Traditional shielding fails spectacularly. Here, heavy metals like lead actually worsen the problem by fragmenting incoming particles into secondary radiation. NASA proposed magnetic deflector shields remain power-hungry fantasies for now. Pharmaceutical approaches show flickers of promise. Compounds like Plex 5622, which temporarily suppress overactive microglia, preserved cognition in irradiated test animals. But drugging astronauts into neurological stability raises ethical quagmires. Should we send explorers who might need daily pills to remember their own mission parameters? Mars missions transform this from a research concern to a potential showstopper. A 6-month transit carries an estimated 13% risk of astronauts developing spaceflight-associated neurocognitive dysfunction, SAND, a newly coined term for the dementia-like symptoms. Surface stays offer little respite. Mars' thin atmosphere blocks only half the radiation, and its lack of a global magnetic field leaves colonists exposed during solar particle events. The cruelest twist, symptoms might not manifest until well into the mission, leaving crews unaware they're deteriorating until they fail a critical task. Historical precedents underscore the danger. Nuclear workers accidentally exposed to neutron radiation, the closest Earth analog to cosmic rays, reported brain fog and memory lapses years later. Soviet cosmonauts on long Salyut missions described unshakable mental fatigue, though secrecy regimes buried most data. The ISS provides scant insight. Its crews enjoy Earth's magnetic umbrella, receiving less neural radiation in a year than a Mars-bound astronaut would in a month. The implications ripple far beyond health charts. A single cognitive lapse during a docking maneuver or habitat repair could doom an entire crew. Mission planners now debate whether to screen astronauts for biomarkers like tau proteins, Alzheimer's indicators. Mid-flight, knowing a positive test might mean aborting the mission. Artificial intelligence could monitor speech patterns for subtle declines, but no algorithm can yet predict when a fading mind might ignore its warnings. This isn't just about surviving space, it's about returning as functional humans. Explorers who land on Mars only to forget their training, their loved ones' faces, or even the taste of Earth's air haven't so much conquered the void as been consumed by it. Until we crack cosmic neuroprotection, every mission beyond Earth's magnetic cradle gambles with the essence of what makes us thinkers, dreamers, and rememberers. The final frontier might not kill us outright. It could just erase us piece by piece, leaving shells of explorers stranded between the stars. Solar panels in space face a slow, invisible assassination, not by design flaws, but by the relentless brutality of the cosmos itself. Those gleaming arrays stretching from spacecraft and stations might look sturdy, but they're locked in a losing battle against two silent killers. Micrometeoroids smaller than a grain of sand and radiation that dismantles their atomic structure one photon at a time. The International Space Station's solar wings, for example, lose up to 2% of their efficiency every year despite looking pristine to the naked eye. That might sound negligible until you realize a 5-year Mars mission could arrive with panels generating 10% less power than at launch, a deficit that could mean the difference between life support stability and a desperate struggle for survival. Micrometeoroid damage plays out like a cosmic shotgun blast in slow motion. At orbital velocities, even a speck of dust hits with the energy of a bullet, vaporizing on impact and carving microscopic craters into solar cells. These pits scatter incoming sunlight instead of absorbing it, turning once smooth surfaces into pockmarked landscapes that trap less energy. The Apollo mission saw this firsthand. Lunar module panels returned with hundreds of microscopic divots after just days of exposure. Modern satellites use protective covers, but nothing stops the tiniest particles. The James Webb Space Telescope's mirrors already show measurable degradation from micrometeoroid strikes despite its million-mile orbit. The cruel irony: solar panels must face the sun to function, making them perpetual bullseyes in an endless shooting gallery. Radiation inflicts a more insidious sabotage. Solar cells rely on carefully engineered semiconductor layers to convert sunlight into electricity, but constant bombardment by protons and cosmic rays knocks atoms out of alignment, creating defects that act like potholes for electrons. Engineers call this displacement damage, the cumulative wreckage of 1 trillion atomic-scale car crashes. The Mars Reconnaissance Orbiter documented this vividly. Its once state-of-the-art panels now produce 30% less power than when they launched in 2005, forcing operators to prioritize which instruments get precious watts. Even more alarming, some radiation effects are temporary, creating phantom recoveries where panels seem to heal during quiet solar periods only to crash again when the next storm hits. Solutions exist in trade-offs as harsh as space itself. Some satellites now employ radiation-hardened cells with thicker semiconductor layers, sacrificing lightweight design for longevity. Others, like the ISS, compensate by oversized arrays, launching with excess capacity knowing it will erode. But these fixes hit limits on crewed missions where every kilogram counts. Proposals for self-healing panels, materials that melt and reform when heated, remain trapped in labs, while rotating arrays that hide during meteor showers add complexity that could fail catastrophically. The bitter reality: we've conquered solar power in space, but not the universe's determination to destroy it. Every watt generated comes with an invisible countdown, a silent race between energy needs and the laws of entropy. The stakes crystallized during a near disaster in 2017, when the ISS temporarily lost half its power after a micrometeoroid severed a critical solar array feed. Astronauts survived on backup systems, but the incident exposed a chilling vulnerability. There's no repairing shredded panels mid-mission. Future lunar bases might dodge some orbital debris, but they'll face a nastier, faux electrostatically charged lunar dust that sticks to panels like corrosive glitter, blotting out sunlight while scouring surfaces. Meanwhile, proposals for Mars colonies rely on solar as primary power, despite the planet's global dust storms that can black out skies for months. Perhaps the ultimate lesson lies in persistence. The Voyager probes, launched in 1977, still communicate with Earth despite their solar panels now operating at 40% efficiency, being bombarded for decades by radiation no Earthbound engineer could fully simulate. Their flickering signals, weaker than a fridge light bulb, testify to both human ingenuity and the cosmos's indifference. Solar power in space isn't just technology, it's a gamble against an environment that never stops trying to turn light into darkness. Even the most advanced spacecraft can become helplessly lost, not for lack of technology, but because the universe itself refuses to hold still. Star trackers, those ultra-sensitive cameras that navigate by locking onto constellations, are only as reliable as the celestial map they reference. Yet stars drift over centuries, supernovas flare unexpectedly, and passing comets masquerade as guideposts, all conspiring to nudge ships toward invisible catastrophe. The margin for error is razor-thin. An error of just 1 arcsecond 1/3600 of a degree translates to being 10 kilometers off course by the time you reach Mars. History records chilling near misses caused by cosmic misdirection. In 1968, the Soviet Zond 5 probe, aimed for a lunar fly-by, nearly missed Earth on its return when its star tracker confused the bright planet Venus for Polaris. Engineers only realized the error after recalculating its trajectory from ground observations, narrowly avoiding a disastrous re-entry over Antarctica instead of the Indian Ocean. Decades later, NASA near Shoemaker spacecraft temporarily lost orientation during its approach to asteroid Eros when sunlight reflecting off the asteroid's surface overwhelmed its star sensors. For 48 harrowing hours, ground controllers manually steered the probe using backup gyroscopes before celestial navigation was restored. The danger compounds exponentially in interstellar space, where familiar constellations warp beyond recognition. Voyager 2's star tracker initially failed upon exiting the heliosphere in 2018, its reference points rendered useless by the unfamiliar star density of the galactic plane. Engineers had to upload entirely new navigation software mid-flight, an 8-hour radio delay each way, to teach the 41-year-old probe how to reorient itself using pulsars as cosmic lighthouses. Had this patch failed, humanity's farthest-flung emissary might have spun silently into oblivion, its antenna no longer pointing home. Modern spacecraft aren't immune to these pitfalls. The James Webb Space Telescope's exquisite sensitivity nearly became its downfall when early tests revealed its star tracker could be blinded by reflected light from its own sunshield. Engineers had to implement strict attendance zones, angles where Webb must never point while searching for guide stars. Even the ISS isn't exempt. In 2007, a software update accidentally reset its star tracker's database to outdated stellar positions, causing temporary thruster firings until astronauts manually uploaded corrected coordinates. Solutions walk a tightrope between innovation and old-school redundancy. New algorithms now compare star patterns against multiple historical catalogs, flagging discrepancies caused by supernovas or instrument errors. The upcoming Lunar Gateway Station will carry 3 independent star trackers from different manufacturers because when your GPS is the Milky Way, you triple-check your maps. Yet the ultimate safeguard remains human ingenuity. Apollo astronauts famously relearned celestial navigation as a last resort, using sextants designed for naval ships to manually verify their computers' star fixes. The cruel irony, spacecraft navigate by the same stars that ancient sailors used, yet the cosmos they chart is far less predictable. Variable stars flicker, binary systems eclipse each other unpredictably, and the Milky Way's rotation slowly drags the celestial sphere out of alignment over millennia. Every star tracker assumes the heavens are fixed, but the universe insists on rewriting the map. Explorers might reach their destination only to find the constellations they left behind have already shifted, leaving them strangers in a sky that no longer matches their charts. Imagine a future where astronauts print replacement parts on demand, no waiting for resupply missions, no cargo constraints. 3D printing in space promises exactly that, but the reality unfolding aboard the International Space Station reveals a darker truth. What works flawlessly on Earth becomes shockingly fragile in orbit. The first zero-gravity 3D printer, installed in 2014, immediately exposed cracks in this utopian vision. A simple extruder nozzle that printed perfect gears in NASA labs jammed repeatedly in space, its melted plastic curling upward instead of flowing smoothly, a quirk of surface tension physics no engineer had fully anticipated. The core issue isn't the printer's mechanics, it's the environment itself. On Earth, gravity helps molten materials settle evenly. In microgravity, liquids behave unpredictably, forming blobs that distort printed layers. Early ISS test prints emerged warped, with structural weaknesses invisible to the naked eye. Astronauts attempting to use a printed wrench watched in dismay as the handle snapped under modest torque, its internal layers riddled with microscopic voids caused by uneven cooling. These aren't just failed prototypes, they're potential death traps when the part in question is an oxygen valve seal or a critical medical tool. Material science adds another layer of peril. Most space-grade printers use thermoplastics like ABS or PI, durable for Earth applications but brittle in space's extreme thermal swings. A printed bracket might function perfectly inside the climate-controlled ISS, but expose it to lunar night temperatures of -170 degrees Celsius and it shatters like glass. NASA Marshall Space Flight Center discovered this brutally when their space-certified filament snapped during thermal vacuum testing, a failure that would have stranded astronauts had it occurred during a real repair. Even successful prints harbor hidden dangers. Earth-based 3D printing relies on post-processing sanding, polishing, or chemical smoothing to remove rough edges that could cause friction or electrical shorts. In space, these finishing steps are nearly impossible. A printed gear with microscopic ridges might seem functional until it's installed in a life support system, where constant vibration wears down adjacent components 5 times faster than expected. The Apollo program avoided this nightmare only because every spare part was machined to micrometer precision before launch, a luxury Mars-bound crews won't have. Software glitches turn these challenges into full-blown crises. File transfer delays between Earth and spacecraft mean last-minute design fixes might arrive too late. In 2019, ISS astronauts attempting to print a radiation shield bracket received corrupted data halfway through the job, resulting in a useless tangle of plastic that wasted 30% of their filament reserves. With no garbage trucks in space, such failures don't just represent lost time, they consume irreplaceable raw materials, risking future repairs. The stakes skyrocket when considering long-duration missions. Current ISS printers can produce only 15% of station components, mostly non-critical items like tool holders. A Mars mission would need 90% part coverage to be viable, printing everything from electrical connectors to surgical staples. NASA's simulated Mars mission in Hawaii saw this fantasy colliding with reality when participants' printer repeatedly failed to produce a working water valve, forcing them to ration drinking supplies. The cruel paradox: the further astronauts travel from Earth, the more they'll need 3D printing, and the less forgiving its failures become. Emerging technologies offer flickers of hope. Metal printers using electron beams rather than melted plastic show promise, though their power demands could drain a spacecraft's batteries. Self-inspecting printers with AI-driven error detection might catch flaws mid-print, but machine learning requires massive datasets, something space missions lack. The ultimate solution may involve embracing imperfection, designing parts that tolerate good enough printing quality rather than demanding Earth-level precision. Until then, every printed screw and gasket remains a gamble, one where the price of failure isn't just a scrapped prototype, but a stranded crew counting down their remaining air. Close quarters and infinite darkness make for a pressure cooker of human emotions, one where even the most disciplined astronauts can snap under the strain. History's most infamous space conflict erupted not in orbit, but in the Arizona desert during the 1993 Biosphere 2 experiment. 8 researchers entered a sealed, self-sustaining habitat simulating off-world living, only to fracture into warring factions within months. One faction hoarded food, another hijacked the mission's communication systems, and all-out psychological warfare erupted when crew members whispered sabotage accusations through the glass to visiting reporters. This wasn't just cabin fever, it was a preview of how isolation amplifies conflicts that would fizzle out on Earth. The International Space Station's carefully curated harmony hides similar tensions simmering beneath the surface. NASA psychologists now classify crew conflicts into predictable phases: the honeymoon period of initial cooperation, followed by irritation spikes around the 2-month mark as novelty wears off. By month 6, even trivial habits, a crewmate's chewing sounds or inconsistent hygiene, can trigger disproportionate rage. The station's solution: a conflict tree protocol that forces crew members to either resolve disputes privately within 24 hours or escalate them to mission control for mediation. But this system nearly collapsed in 2007 when 2 astronauts refused to speak to each other for days, forcing a third to act as their unwilling messenger during critical operations. Cultural differences add another layer of volatility. Russian cosmonauts traditionally begin meals with bread and salt, a ritual Americans often disregard as frivolous. Small slights accumulate: a misplaced tool blamed on the American side, or a sarcastic comment lost in translation. NASA archival recordings reveal moments of shocking vitriol, like the 1995 Mir incident where a sleep-deprived astronaut screamed at ground controllers to stop yanking my chain over minor requests. These outbursts aren't mere personality clashes, they're warning flares for Mars missions where real-time mediation will be impossible. The most insidious conflicts aren't the explosive ones, but the silent grudges that fester. During the 1-year ISS mission, astronaut Scott Kelly and cosmonaut Mikhail Kornienko maintained flawless professionalism. Yet Kelly's memoir later revealed months of unspoken resentment over chore distribution. Such buried tensions become dangerous when crews avoid confronting issues to preserve team cohesion, creating a pressure that eventually detonates during emergencies. Antarctic winter over crews, Earth's closest analog to space isolation, show this vividly. Researchers at the Amundsen Scott Station once split into rival gangs who communicated only via passive-aggressive sticky notes for weeks. Modern countermeasures walk a tightrope between therapy and pragmatism. Crews now undergo intensive pre-mission personality mapping, pairing individuals whose psychological profiles show complementary, not identical traits. The ISS employs mood lighting to simulate dawn/dusk cycles that regulate tempers, while virtual reality escape pods let astronauts briefly immerse in forest or beach scenes. Yet the ultimate solution might be counterintuitive, allowing controlled conflict. NASA's recent Hera habitat experiments found crews who aired grievances early via structured debates performed better long-term than those who suppressed frustrations. Sometimes the safest teams aren't the happiest, just the ones who know where the cracks are before the hull breaches. The terrifying lesson from every confined environment, from submarines to space stations, is that humans don't break down despite their training, they break down because of it. The very discipline that makes astronauts exceptional also masks their stress until it's too late. Future Mars colonists won't just need engineers and biologists, they'll need peacemakers fluent in the unspoken rules of conflict in a world where walking away means stepping into a lifeless void. Harmony in space isn't about eliminating tension, it's about learning to navigate fault lines when there's literally no space to cool off. Re-entering Earth's atmosphere is the ultimate high-stakes gamble, a white-knuckle ride where a spacecraft must bleed off orbital velocity by transforming itself into a blazing meteor. The numbers defy belief: 30 times the speed of sound, temperatures hot enough to vaporize steel, and forces that could crush an untrained body like a soda can. Yet this fiery gauntlet conceals dangers far beyond the obvious flames, from microscopic cracks in heat shields to the insidious blackout period, where screaming plasma cuts all communication with the ground. The Columbia disaster in 2003 laid bare these risks with horrifying clarity. Investigators later reconstructed the chain of failure. A suitcase-sized chunk of insulating foam had broken loose during launch, punching a basketball-sized hole in the shuttle's left wing. For 16 days, the crew orbited unaware as this invisible wound waited to betray them. During re-entry, superheated plasma, a soup of ionized gas reaching 3,000 degrees, seeped through the breach like a blowtorch, melting internal aluminum struts until the wing disintegrated at 20 times the speed of sound. The terrifying twist: Columbia's computers registered the damage through erratic sensor readings minutes before breakup, but by then, no escape existed. Modern capsules like SpaceX's Crew Dragon now carry reinforced carbon-carbon heat shields and triple redundant parachutes, yet the ghosts of Columbia linger in every pre-re-entry inspection checklist. Heat shield erosion remains the silent saboteur of safe returns. The Apollo capsules used ablative shields materials designed to char and flake away, carrying heat with them. Too much erosion and the spacecraft burns through, too little and heat doesn't dissipate fast enough. Engineers on Apollo 13 faced this nightmare when the explosion-damaged service module left them uncertain if their command module shield had been compromised. Their desperate jury rigging worked, but today's newer phenolic-impregnated carbon ablator Pika-X shields face subtler threats. Microscopic voids in the material, invisible to quality checks, can create weak spots that fail catastrophically under re-entry loads. In 2014, an unmanned SpaceX Dragon capsule survived re-entry with a heat shield pockmarked by pinhole burns, later traced to trapped gas bubbles in the manufacturing process. Had those voids clustered differently, the results could have mirrored Columbia's fate. The blackout period adds another layer of terror. As ionized plasma engulfs a descending spacecraft, radio signals become impossible for up to 7 minutes, precisely when critical course corrections might be needed. Vostok 1's Yuri Gagarin experienced this helplessness firsthand in 1961, when his capsule's automatic re-entry system failed to separate the equipment module cleanly. Tethered together, the two sections entered a violent spin until aerodynamic forces finally ripped them apart, subjecting Gagarin to 8 Gs, nearly double the expected load. Today's astronauts train for similar contingencies using manual, role reversal techniques to stabilize tumbling capsules, but no amount of practice guarantees control when plasma turns your vehicle into a blind, falling brick. Perhaps the cruelest irony lies in re-entry's final moments. After surviving infernal temperatures, a spacecraft can still be doomed by something as mundane as a tangled parachute. In 1967, cosmonaut Vladimir Komarov perished when Soyuz 1's main chute failed and the reserve line twisted around the collapsing canopy. Modern systems use pyrotechnic cutters to jettison malfunctioning chutes, but wind shear remains an unpredictable killer. Orion capsules now test their parachutes over desert and ocean, accounting for everything from monsoons to failed altimeter sensors. Yet as Apollo 15 demonstrated when one of its 3 chutes collapsed during splashdown, even flawless engineering bows to chance, the ultimate lesson of re-entry is humility. For all our advances, returning from space still requires surrendering to laws of physics written in fire. Every successful splashdown is a temporary victory against chaos, a reminder that the cosmos never truly lets go without extracting a price. Those who venture beyond Earth must pass through this crucible twice, once on the way up and once on the way home. Only one guarantees a mortal audience with the flames. From the silent creep of cosmic radiation to the psychological toll of endless isolation, space is a minefield of hidden dangers, each capable of turning exploration into tragedy. Imagine floating through a universe where solar flares cook electronics without warning, where moon dust slices through skin like microscopic glass, where even a fleck of paint becomes a high-velocity bullet. These aren't hypotheticals, they're realities astronauts face daily, from muscle wasting in microgravity to the eerie hallucinations brought on by sensory deprivation. The void doesn't fight fair. It attacks from every angle, warping metal with temperature extremes, scrambling navigation with electromagnetic storms, and eroding bones faster than aging. Yet for every danger, scientists are forging solutions as bold as the threats themselves. Teams at NASA and private labs are testing magnetic force fields to deflect radiation, while bioengineers grow muscle-preserving drugs tailored for zero-G. Lunar habitats now prototype self-healing hulls to resist meteoroid strikes, and AI-driven psychologists monitor astronaut mental health through speech patterns. Even the most insidious threats like time dilation's cognitive toll or 3D printing failures are being outpaced by innovations. The James Webb Space Telescope's sun shield, once deemed impossible, now floats flawlessly 1,000,000 miles away, proving that humanity's ingenuity often outpaces the universe's cruelty. The next chapter of space exploration won't just be about surviving these dangers, it'll be about rewriting the rules. Imagine Mars bases shielded by artificial magnetospheres, or astronauts drinking water purified by nanofilters tougher than anything on Earth. Every risk we uncover is a puzzle begging to be solved, and the solutions will ripple far beyond space, revolutionizing medicine, materials, and even how we think about life on our own planet. So as we stand on the edge of this cosmic frontier, let's not just marvel at the perils, let's tackle them together. Which danger surprised you the most? Drop a comment below and keep looking up. The universe is waiting, and it's far too wild to face alone.